Hello all, welcome back to Climate Dynamics. In today's lecture, we'll be talking about the Earth's paleoclimate, that is, the record of the Earth's climate going back in time. The reading for today's lecture is Marshall and Plum, chapter 12.3. In today's lecture, we'll be defining temperature proxy, dendroclimatology, delta 18O, and Milankovich cycles. We'll be answering these questions. How have we developed Earth's historical temperature record? What are the major factors affecting Earth's temperatures in the past? In the historical record, why does carbon dioxide tend to lag temperature changes? And what are the characteristics of Earth's past greenhouse and glacial climates? This lecture is broken up into two parts. In the first part, we'll talk about reconstructing the Earth's historical temperature record. Okay, considering that we have only been making methodical records of temperature starting in 1850, in order to reconstruct temperatures before this time, we need to rely on proxies, that is, secondary sources for assessing the Earth's temperature. Formally, a temperature proxy is a measurement that can be used to calculate the value of temperature, for example when these direct measurements are not available. Proxies for temperature include tree ring records, a field known as dendroclimatology, ice cores, including the study of trapped air bubbles and ice layer thickness, geological evidence in ancient coal beds, sand dunes, and fossils, documents that concern droughts, floods, and crop yields from Earth's anthropogenic record, the chemistry of lake bottom sediment and soil deposits, and pollens in deep ice caves, soil deposits, and sea sediments. New proxies are being developed every year by researchers in order to better understand Earth's climate history. We're going to focus on three of those proxy records in this lecture. First, we'll talk about dendroclimatology, then we'll talk about ice cores, and finally, we'll talk about ocean bottom sediment. Formally, dendroclimatology refers to the study of Earth's climate through the study of tree rings. These tree rings can allow us to look back over 7,000 years in the Earth's climate history, although uncertainty grows beyond about 1,000 years in the past. Since we know trees grow one ring per year, the distance between these rings can say something about whether or not climate conditions were favorable or unfavorable towards growth. In particular, they can tell you about temperature and moisture fluctuations related to climate variability. Here's an example cross-section from a tree. Looking at this, can you recognize which 2 years were the warmest years and which was the coolest year? If you look closely, you'll notice that tree rings in years 5 and 7 are somewhat thicker than their counterparts. And also, the tree ring in year 6 was abnormally narrow. Consequently, we can ascertain that climate conditions were favorable in years 5 and 7 and that they were unfavorable in year 6. By combining evidence from multiple trees within a particular area, we can then build stronger statistical evidence towards climatic factors that contribute towards growth of trees within that region. A recent paper by Williams et al., published in 2020, showed that tree ring records could be used to reconstruct temperatures and soil moisture in the U.S. West over the past 1,200 years. Their results showed that periodic occurrence of megadroughts was common in this region, that is, periods of particularly prolonged dry conditions, including extreme droughts that occurred in the 1500s and from the mid-1200s past the 1300s. These megadroughts are particularly concerning and useful for understanding future planning of water resources. Our second proxy that we're going to examine is ice core records. Much of our knowledge of past climates extending back over 800,000 years comes from the investigation of ice cores. The thickness of each layer of ice can give us clues about the amount of precipitation that occurred in that season. Further, air bubbles that are trapped in the ice can give us clues to the chemistry of the atmosphere at that time. There are various sites all over the world that can be used to extract ice cores. We have sites located in the northern hemisphere in Greenland, northern Russia, and in Alaska. We also have sites in the Himalayas, in the Kilimanjaro ice fields approximately along the equator, as well as various sites in the Andes. Our longest ice core records, though, come from Antarctica. Antarctic sites include Dome A, Dome C, Vostok, and Taylor Dome. Most recently, a 2.7 million year old ice core was recently extracted from the Allen Hills, located near Taylor Dome. Also, the Vostok ice core, which will be the focus of some of our later discussion, gives us an 800,000-year glimpse into the Earth's climate history. Greenland also has a number of locations which can be used to extract ice core records and learn about the climate of the northern hemisphere. The oldest Greenland ice cores date to about 130,000 years before present. Our third proxy is ocean sediments. Ocean sediments can be used to extract climate history far beyond those of the ice core record. In particular, these ocean sediments can be used to track back temperatures as far back as 540 million years ago, back to the advent of life on Earth. Ocean sediment records work as follows. Normal oxygen, we know, contains 8 protons and 8 neutrons. This is an isotope of oxygen known as 16O. However, a small fraction, approximately 1 in 1,000, of oxygen atoms contain 8 protons and 10 neutrons. This is a slightly heavier oxygen atom. This particular isotope is referred to as 18O. Thus, there are 2 major isotopes of oxygen, 16O and 18O, with 18O being the heavier of the 2. Because 18O is heavier, it also requires more energy for it to evaporate. You can imagine, looking back at our kinetic energy understanding of temperature, that more kinetic energy would be needed in order to make a heavier object move fast enough to leave the surface of the liquid. Thus, 16O will evaporate more readily than 18O because it is lighter. During the ice ages, this 16O rich water is typically stored in glaciers. Namely, because the 16O rich water evaporates more readily into the atmosphere, it can then lead to precipitation in colder regions, and thus is the major contributor to accumulation in our global ice sheets. However, if that 16O water is trapped within the cryosphere, this then removes it from the ocean and increases the concentration of 18O in the oceans. It is in these cold times that delta 18O is high in the oceans. Here, the delta denotes the relative concentration. If we look at the ratio of 16O to 18O in ocean fossils and other ocean sediments, which are derived from oxygen atoms in the ocean, that is, this biota grows and extracts oxygen as it grows from the ocean, then this can give us clues about global temperatures at the time. The Earth's temperature record, then, over these geologic timescales is measured using this quantity delta 18O. Formally defined, delta 18O is the difference in the 18O divided by 16O ratio between a sample and an associated standard normalized by that standard. That is, a value of 0 corresponds to a ratio which is exactly the same as that of the standard. Typically, this is expressed in per mil. So the formula for delta 18O is given here. This ratio has been observed to be closely correlated with temperature because of the preferential evaporation of 16O. It can be measured in calcium carbonate shells from the fossil record. Ignoring the effects of salinity, a 0.22 per mil increase in delta 18O is equivalent to 1 degree of cooling. Here's a depiction of why 18O becomes more concentrated in ocean water during colder glacial periods. During warm periods, we typically have high 16O in the oceans. This tends to evaporate more readily into the atmosphere, and so the atmosphere carries 16O rich water. This then precipitates over land and can accumulate either in liquid precipitation or in solid precipitation, namely in the cryosphere. During warm conditions, the cryosphere is not able to accumulate substantially, and so the 16O rich water then simply runs off back to the ocean, returning it to the ocean and maintaining a relatively consistent concentration. During these warmer periods, ocean fossils then have elevated levels of 16O. However, during the cold glacial periods, the evaporation of 16O water means that the colder conditions will lead to trapping of the 16O rich water in land ice. That is, the growing cryosphere will preferentially accumulate 16O rich water. Because melting is blocked during these colder periods, the 16O rich water cannot return to the ocean, and so 18O levels increase in the ocean. Thus, we find that during these cold glacial periods, ocean fossils have elevated levels of 18O. Okay, so let's use these three proxies in order to look more closely at the Earth's temperature record. Here is the Earth's temperature record for the past 1,000 years or so. What we see is relatively consistent temperatures. Here, the temperatures have been normalized to the 1961 to 1990 average. Since temperatures during this period are much warmer than the historical record, we see that most temperatures fall below the zero line. There is, however, growing uncertainty as you go farther into the past. After about 1850, as mentioned earlier, we have solid records taken from exact measurements using thermometers. However, before that, we rely on these proxy records. What we see in these temperature records is what is known as the hockey stick. That is, we see relatively consistent temperatures for most of the Earth's history over the past 1,000 years, except for the past 100 or so years, where there has been a dramatic increase in average temperatures. This increase in temperatures is associated with increasing carbon dioxide concentrations in the atmosphere because of anthropogenic activities. We'll discuss this next time in our class on climate change. However, before that, we also see substantial variations in the Earth's temperature record, associated with natural climate variability. In particular, between 1300 and 1850, the Earth experienced a period known as the Little Ice Age, that is, a period of abnormally low temperatures. Before that, from 950 to about 1250 AD, it experienced a period known as the Medieval Warm Period, that is, slightly elevated temperatures. If we consider the Earth's history over the past 20,000 years, we can actually see a transition between two climatological states. The Holocene, which is associated with the rise of civilization, was a period of relatively stable temperatures, and also relatively warm temperatures. The Holocene is a so-called interglacial period, that is a period between glacial phases. Before that was the Pleistocene. The Pleistocene was a glacial period, that is a period of relatively cold temperatures associated with widespread extension of the northern polar ice caps. This was a period in which much of North America was covered with ice. It also was associated with the LGM, which was the last glacial maximum. Between the Pleistocene and the Holocene, we had a transition period. The transition period was associated with first a period of warmer temperatures, known as the Bulling-Alleride, and a second period known as the Younger Dryas. During the Bulling-Alleride, the melt of the North American ice sheet led to an injection of fresh water into the North Atlantic. As discussed in the thermocline lecture, this led to a shutdown of the thermocline because it prevented deep convection from occurring in the North Atlantic. Consequently, warmer waters were not brought into this region, and so we had a climate response which led to relatively colder conditions then through the Arctic. This period was known as the Younger Dryas. After the Younger Dryas, temperatures recovered, and we entered into the period of the Holocene. If we now use ice core records to go back 800,000 years before present, we can see that these glacial and interglacial phases of the Earth actually were fairly common. The Earth actually flip-flopped between both glacial and interglacial stages. Using carbon dioxide records, which were extracted from air bubbles within ice cores, we can actually find close correspondence between the carbon dioxide concentration of the atmosphere and Earth's temperatures. Namely, during periods of high carbon dioxide concentration, we had these interglacial phases associated with relatively warm temperatures. On the other hand, lower carbon dioxide concentrations are associated with the glacial phases, or lower temperatures. The carbon dioxide concentration in the Earth's atmosphere over the past 800,000 years has largely only varied between approximately 180 parts per million during glacial periods and 280 parts per million during interglacial periods. It's only recently that we've seen carbon dioxide concentrations exceeding 280 parts per million, again because of human activity. Throughout the Pleistocene, we saw again this transition between glacial and interglacial periods. Examining the period of these oscillations, we find that over the 800,000-year record that there was approximately 100,000 years between peaks. That is, there was a period of about 100,000 years associated with this flip between glacial and interglacial periods. The reason for this can be traced back to variations in the Earth's orbital parameters. In particular, there are three key characteristics of the Earth's orbit that play a role in the amount of insolation the Earth receives. The first is the eccentricity of the Earth's orbit. This varies on approximately 100,000 to 400,000 kiloyear timescales, from almost zero, which corresponds to a roughly circular orbit around the Sun, to 0.07, that is, a very slight ellipse. When the Earth is in an elliptical pattern, then there is substantial seasonal variation in the amount of insolation received by the planet. Note that at present, the perihelion of the Earth's orbit falls on January 3rd, so northern hemisphere winter and southern hemisphere summer are slightly warmer than winter-summer in the opposite hemisphere. We actually saw that earlier in this class when we talked about insolation received on the planet as a function of season. The second orbital parameter that's important for determining insolation is the change in tilt of the Earth's spin axis. This is known as the obliquity, and it varies between 22.1 degrees and 24.5 degrees on a timescale of approximately 41,000 years. The final orbital parameter is the direction of the Earth's spin vector, and this is associated with a precession of the spin vector with a period of approximately 23,000 years. Note that the precession actually determines the seasonality of the planet. That is, 23,000 years from now and 23,000 years in the past, the seasons were actually in reverse, with northern hemisphere summer occurring during December, January, February, and northern hemisphere winter occurring during June, July, August. The orbital impacts on insolation are known collectively as the Milankovich cycles of the Earth. Formally, these Milankovich cycles refer to the oscillations in the Earth's orbital parameters that affect its climate over thousands of years. Again, they include the eccentricity, obliquity, precession, and other orbital parameters of the planet. In this plot, on the top three lines, we see the variations in precession, inclination, and eccentricity over the past million years. These combined then give variations in solar forcing. In particular, we're interested in the solar forcing that is experienced at the edge of the ice sheets. It is in this region where the solar forcing plays a very important role in determining the sea ice and ice sheet extent. The ice sheet extent then plays a role in determining the albedo of the planet, and so variations in the amount of solar forcing received in this region can then lead to ice-albedo feedbacks, which can lead to warming or cooling of the planet. The solar forcing that is experienced at 68 degrees north in the summertime can vary between 440 watts per meter squared to 540 watts per meter squared depending on the orbital parameters of the planet. The resulting variations, then, are responsible for driving the Earth towards warm or cold climate states. Here we see the Milankovich cycles of the Earth imposed with the obliquity contribution in green. Although there is substantial variation, there is a regular period associated with these cycles. Here in particular, we see the variations in summer solstice insolation at 65 degrees north due to the various components of the Milankovich cycle. Variations in total insolation are as large as 130 watts per meter squared, or about 25% of the total amount of insolation received at that latitude. This is of course very substantial and can greatly change the energy balance of the Earth's system. In the current period, we see that we are actually in a time of relatively stable orbital parameters, and we expect that the orbital contribution to be fairly stable for the next 50,000 years or so. However, there have been periods in the past where there have been rapid variations in these orbital parameters that are then responsible for potentially driving us towards interglacial or glacial states. If we look at the Milankovich cycles for the past 5.5 million years, and the corresponding changes in temperatures measured through the Vostok ice core, what we see is a 100,000 year cycle that extends to about 1 million years ago, and before that, a temperature cycle that had a period of about 41,000 years. This 40,000 year cycle is more closely related to changes in the obliquity of the Earth's orbit, and was responsible for driving temperature changes of 6 to 7 degrees. More recently, over the past million years or so, this 100,000 year cycle was related to changes in eccentricity. However, the reason for the switch from a dependence on obliquity to a dependence on eccentricity is not well known. If you look closely at the relationship between carbon dioxide and temperatures, you might notice that carbon dioxide maxima actually tends to lag slightly behind that of temperature. Namely, even as temperatures decay at the end of these interglacial periods, carbon dioxide concentrations tend to remain high. Also, carbon dioxide tends to peak approximately 800 years after the peaking in temperatures. This has been latched onto in the past in order to argue against the modern theory of climate change. However, we'll see that the underlying mechanism is actually the same. Here is a depiction, a flowchart, showing the temperature carbon dioxide feedback. Under warming conditions, some sort of external forcing can induce slightly warmer oceanic temperatures, or for instance can cause retreat of ice sheets, which then expose the ocean to the atmosphere, and consequently solar insolation can lead to warming of that near sea ice latitude. Increased ocean temperatures are associated with lower solubility of carbon dioxide, much in the same way that a warm soda can hold less carbon dioxide and tends to taste flat. Because carbon dioxide solubility is reduced in the warmer ocean waters, the ocean releases carbon dioxide to the atmosphere, driving up carbon dioxide concentrations. Thus, the higher carbon dioxide concentrations drive the greenhouse effect, which can in turn then drive warmer oceanic temperatures. This positive feedback loop is then one of the contributors to driving the Earth out of a glacial phase. Note that here the orbital forcing is responsible for driving the warmer oceanic temperatures, which then reduces the solubility. However, the anthropogenic element, that is, if we consider the modern theory of climate change, is associated with the injection of carbon dioxide into the atmosphere, so it effectively enters the feedback loop from a different state than the orbital forcing. Nonetheless, what we see is that if you have a warmer oceanic temperature, then that can result in the release of carbon dioxide, thus driving up atmospheric carbon dioxide concentrations. In the cooling phase, a change in orbital forcing can drive us back into a glacial state by cooling oceanic temperatures, leading to an increase in carbon dioxide solubility within the oceans, which leads to an increase in absorption of carbon dioxide from the atmosphere into the oceans, thus driving down atmospheric carbon dioxide concentrations, reducing greenhouse effect, and thus leading to cooling of the surface. Again, this is basically just running the positive feedback loop in reverse. If we use the ice core record to look back to the beginning of Antarctic reglaciation and use ocean sediments to look back even farther, we can get a pretty good picture of what the past 65 million years were of the Earth's temperature record. What we see are some really interesting phases of the Earth's climate. First of all, most recently we see these flips between the glacial and interglacial states of the climate system. If we go back to about 12 million years ago, we enter into a time when the Antarctic was reglaciating. That is, before this time, the Antarctic was ice-free. This accumulation of snow over the Antarctic drove the Ice-Albedo feedback. That is, it drove up the albedo of the planet, thus contributing to further cooling of the Antarctic region. Thus, the reglaciation period for the Antarctic was fairly rapid. That is, we saw a change in the climate state from an ice-free Arctic to a glaciated Arctic over only a million years or so. The period of the ice-free Arctic extended from about 25 million years ago to about 12 million years ago. But immediately before that, we also had a state where the Antarctic was glaciated. That extended to about 34 million years ago. Before that was the Paleocene and the Eocene. These periods were associated with relatively warm temperatures, much warmer than present. In particular, there was a period at the end of the Paleocene, known as the Paleocene-Eocene thermal maximum, where deep ocean temperatures were probably closer to about 16 degrees, compared to about the 2 degrees observed today. This was associated with cold-blooded creatures that actually lived in the Arctic, as well as palm trees in that region. So the region was relatively tropical by comparison to today. Obviously, if we look back in the Earth's deep history, we find periods that were substantially warmer than what we experience today. By studying these periods, perhaps we can understand more what future climate states of the Earth may be like. As mentioned on the last slide, the Ice-Albedo feedback was important for driving the Earth system between two climate states associated with a glaciated Antarctic and an unglaciated Arctic, or a ice-free Arctic. This feedback mechanism allowed the system to swap between these two states. If we have some sort of external or orbital forcing that can drive warmer ocean temperatures, these warmer ocean temperatures can lead to a retreat of the polar ice caps. The retreat of the ice caps then decreases the global albedo, leading to more radiation absorbed at the surface, which leads to warmer ocean temperatures. Like all the positive feedback loops that we've discussed previously, this can also be run in advance. Namely, slightly colder ocean temperatures can lead to an expansion of polar ice caps, which can increase global albedo, which can then lead to less radiation absorbed at the surface, further decreasing temperatures. By using this feedback mechanism, the Earth's system then can switch between glaciated and non-glaciated states. As mentioned earlier in this lecture, by using fossil records and ocean sediments, we can actually trace the Earth's temperature record back to about 550 million years ago, in the Cambrian period. What we see is that the Earth has experienced really substantial shifts between warmer temperatures and cooler temperatures. The average temperature of the planet varies between approximately about 12 degrees Celsius and 22 degrees Celsius, where most recently we find ourselves in a relatively cold period with lower temperatures. However, there is also evidence of prolonged glacial periods that have extended through the Earth's history, lasting tens of millions of years. During these periods, there is geologic evidence supporting widespread ice over the Earth's surface. It is unsurprising that these periods occur during times when the Earth's temperatures are at their lowest points. However, if one considers this temperature record in light of amount of solar output, in particular, noting the fact that solar output has generally trended upward over time, it is perhaps a little surprising that the variations have remained roughly constrained to the same interval, between approximately 12 degrees Celsius and 22 degrees Celsius global average temperature. In order to understand this in more detail, we must understand the historic carbon dioxide record. The top plot here shows atmospheric carbon dioxide concentrations in parts per million over the past 550 million years of the Earth's history. What we see is that at present, carbon dioxide concentrations are relatively low compared to what they have been historically. In particular, during the time of dinosaurs on the planet, carbon dioxide concentrations were between about 1,000 and 2,000 parts per million. This also corresponded to relatively warm surface temperatures, and again conditions, as discussed earlier, which resulted in palm trees in the Arctic and relatively warm ocean temperatures. There was a period of relatively cool temperatures at about 300 million years ago, associated with widespread glaciation. But before that, carbon dioxide concentrations were very high, reaching, in some cases, in excess of 6,000 parts per million. The high carbon dioxide concentrations that existed in the early history of the Earth were necessary in order to provide a greenhouse effect capable of compensating the relatively low solar output that occurred during this period. Because of the high carbon dioxide concentrations in the Earth's atmosphere, relatively low solar output nonetheless led to relatively tolerable surface conditions. In particular, the carbon dioxide prevented widespread freezing of the Earth's surface, which would have been disastrous to life. In the bottom plot, we consider total radiative forcing, that is, the combination of radiative forcing because of the greenhouse effect, because of carbon dioxide, and because of changes in solar radiation. What we see is that the total radiative forcing in terms of watts per meter squared actually remained fairly constant over the Earth's history, only varying plus or minus 8 watts per meter squared. Because of this, temperatures generally were only 5 to 10 degrees warmer than present, even when carbon dioxide concentrations were in excess of 3,000 parts per million. Okay, let's consider a couple of the climate states that have existed through the Earth's history. In particular, let's focus on greenhouse climates. The most recent example of a greenhouse climate occurred during the Cretaceous period, where global average surface temperatures approached closer to 22 degrees Celsius. During these periods, the Earth had no ice caps, that is, it was entirely ice-free. Sea levels were 100 to 200 meters higher due to melting of these land ice caps and because of thermal expansion of the ocean. As mentioned earlier, during these periods, broad-leaved plants, dinosaurs, and turtles lived north of the Arctic Circle. Notably, these are of course cold-blooded creatures, and so they require a relatively warm environment in order to live. During this particular period, carbon dioxide was thought to be about 5 times pre-industrial. Here's a map showing the paleogeography of the late Cretaceous, that is, 90 million years ago. Besides the fact that the continents have since moved around, what we see is that because of the higher sea level, much of the inland regions of these continents have been flooded and are replaced with inland seas. Consequently, much more of the Earth's surface is covered in ocean. Clearly, the ocean circulations that existed at this time would have been substantially different than we see today. In particular, think about how much of the ocean circulations depend on the underlying geography. Things like western boundary currents and the thermohaline are highly dependent on the current structure of the Earth's continents. With more of the land flooded, we would have more capacity for warmer ocean waters to circulate freely through the Earth, consequently leading to a more homogeneous temperature over the whole planet. Now that we've considered greenhouse climates, let's consider the opposite, namely glacial climates. The last example of a glacial climate occurred approximately 21,000 years ago. During this time, much of the ocean water was locked up in the form of land ice. This led to much lower sea surface heights, on the order of 120 to 130 meters lower than they are today. Consequently, we see features like the Bering Strait now closed, replaced with the Bering Land Bridge. This is presumed to have been the method by which humans then moved from Asia to North America. During this time, the Laurentide ice sheet covered much of North America, being 2 miles or 3.2 kilometers thick in some locations. These massive ice sheets then carved out much of the landscape over the continents, leaving behind things like the Great Lakes in North America. Massive ice sheets covered other parts of the continents of the world as well. In general, conditions during this time were windy, cold, and arid. Recall that the cooler air temperatures of this time would be able to hold less moisture, simply because of the Clausius-Clapeyron relationship. Consequently, during this time, the overall climate was much more arid than it was today. If we look back farther through the geologic climate record, we know that some of the major changes that have occurred in the Earth's climate over the geologic record are often associated with movement of the Earth's tectonic plates. The figure here on the right shows how those tectonic plates have varied over time, going back 250 million years ago to the Permian, when effectively the world consisted of a single continent and a massive ocean. Over time, those continents have broken up and have spread to their locations at present day. The spread of the continents at present day are associated with much less free movement of ocean waters, and hence less capacity for the ocean to distribute heat more evenly over the Earth's surface. There are changes in the continental structure of the planet that have been known to affect climate. For instance, it's hypothesized that the closure of the Isthmus of Panama, that is the connection between North America and South America, by plate tectonics, is thought to be the driver of the modern ice age, by preventing the oceanic distribution of heat from the Pacific Ocean into the Atlantic Basin. Also, the opening of the Drake Passage at the tip of South America led to the formation of the Antarctic Circumpolar Current, which then led to isolation of Antarctica and its eventual glaciation. Here, the isolation refers to the fact that because of the strong zonal currents that exist in the Antarctic Circumpolar Current, it was much more difficult for warmer waters from the equatorial or subtropical regions to puncture south of the Antarctic Circle. Consequently, this region became largely isolated, and sea ice was left to grow freely. Another possible connection between the geologic record and climate occurred when the Bering Strait was much wider than present. That is, during the Cretaceous, we had, of course, much higher sea levels, which meant that the Bering Strait was much wider. During this period, the Antarctic Ocean was much more accessible by warm ocean currents, and so warmer waters from the Pacific could readily move into the Arctic, and thus prevented the formation of sea ice in this region, as well as drove warmer temperatures at depth. However, it is worth noting that although many theories have been put forward to account for the shape and the period of these long-term climate oscillations, none yet exists that can exactly account for the observed record. And so research is ongoing to better understand our planet's history. All right, that's everything for today. Next time we'll be talking about climate change.